In this short video, I wanted to give a brief recollection about this notion of categories, which was already discussed in the commutative algebra course. And so as a kind of motivation, I want to observe that many areas of mathematics are centered around some class of objects and morphisms between them. By this I mean, for example, in linear algebra, you define the notion of a vector space, and then you start studying linear maps between these vector spaces. In topology, you have topological spaces and look at continuous maps. In group theory, you define what a group is, and then you define what a group homomorphism is. And in the commutative algebra lecture, we had both kind of rings and then ring homomorphisms, and R modules and R module homomorphisms between them. So in all of these cases, had some kind of gadget and then some kind of map between them, which had good properties. And the notion of a category captures some basic familiarities between all of these different examples. And so the definition is that the category C is the data of first a collection or a class of objects A and C. And then for any pair A comma B, a set of morphisms denoted like this between them. A priori, this is just some abstract set. And here I say set, so to be fully honest, what I define for you is really called a locally small category, because these morphisms form a set. In general, these could also form one of these classes, but never mind about this. So we have a set of morphisms from A to B, and then what we like to do with morphisms is compose them. So from this product of morphisms from A to B and morphisms from B to C, we want to take such a pair and take the composition, which should give us a morphism from A to C. That's one of the basic operations. And also, inside the morphisms from A to A, we want to have a distinguished identity morphism. And a priori, these are all just kind of abstract things with names being kind of suggestive. And the properties we require is that the composition should be associative. It shouldn't matter in which order we take the composition here. And second of all, we want that the identity morphisms are both left and right identities. So if you have phi and you pre-compose it with the identity, you get phi. And similarly, if you post-compose with the identity of the target. And that's it. That's already the data of the category. And some of the advantages of this language is that, for example, it automatically defines some notions for you, like the notion of an isomorphism, because you can say phi in the morphisms from A to B is an isomorphism if and only if there exists psi in the morphisms in the opposite direction, such that if you compose it like this, you get the identity of A. If you compose in the opposite way, you get the identity of B. So it's left and right inverse. And the cool thing here is that you just had to define what morphism means, and then the notion of isomorphism was for free. Whereas, I mean, in a lot of the classes which you have seen before, probably the isomorphism was defined separately. But in fact, if you use this language of categories, you don't have to define it separately. It's given to you for free. And the second, we're not going to use this so much, but it is true that you can use this language to make connections between different areas of mathematics via functors. So functor goes from one category to another. It sends the objects here to objects here. And if you have two objects and a morphism between them, it sends this to a morphism between the target objects. And this should kind of send the identity to identity and should send compositions to the corresponding compositions. So that's just in words what a functor is. But to give an example, if you have seen some lecture like algebraic topology, or maybe you did this in a topology lecture, what you can do is take the category of topological spaces with continuous maps. And there's a functor to the category of groups with group homomorphisms, which takes the topological space X and sends it to the homology group H lower star of X. if you haven't seen it, don't worry so much about it. But just kind of abstractly, you can see that there is this H lower star which takes any topological space and associates a group to it. And that means that if you have nice theorems in group theory, you can hope that maybe they tell you something about topology. So that's a very convenient language. And to conclude the video, I just want to point out that large parts of our course here, the algebraic geometry course, are about defining categories of nice geometric objects. So for example, the entire chapters 1 to 4 of the course are basically just about defining the category of affine varieties. We have already seen its objects, the affine varieties X, and in chapter 4, we're concerned then about what are the morphisms in this category. And this is then basically just the start, because then we start enlarging this category. We allow more and more general objects. So for example, not just affine varieties, but arbitrary varieties in chapter 5. And then we go again a bit more special and look at the special case of varieties called projective varieties in chapter 6 to 7. And then that's the setting which we can comfortably work in for some time, and we study some properties of this. But then towards chapter 12, towards the end of the course, we also define these notions of affine schemes and then schemes. And that's the kind of the big goal of the course, is to say what is a scheme, because that is the modern language in which algebraic geometry happens. But for now, this is still far away. And the goal of the next chapter is just taking these affine varieties, which we already have, and defining what does it mean to be a morphism from X to Y.